GEOGADKA. Webinaria.
Good evening, everyone. My name is Vineet. I'm working in the Department of Polar and Marine Research in the Institute of Geophysics. And this talk is a general talk about the ocean's contribution to climate change in Arctic. And I will give some specific examples from Svalbard. So the talk has three parts. In the first part, which is also the longest part, I will introduce climate change in general, some of the feedback processes that are causing enhanced warming in Arctic, and I will talk about the role of oceans in such feedbacks. The second part will introduce some basic tools in oceanography, specifically physical oceanography, and what I mean in terms of physical oceanography is like observation of physical properties of water, which is mainly temperature and salinity. And in the last part, I will show some of our observations from the Hornsund Fjord in Svalbard. So let us start with the first part. When you hear or read about the climate change in Arctic, you will likely come across the term called Arctic amplification, which is basically the term which refers to enhanced warming north of 67° north compared to the rest of the world. So if you see in the plot here, the red one shows the temperature anomalies in the Arctic, and the blue line is for the global rate. And you see that in the last few decades, temperature in the Arctics have risen about 2 to 3 times the pace of the rest of the world. So what causes this enhanced warming in Arctic? So there are several feedback cycles which contribute to this warming. And what is meant by feedback is that the warming causes some processes which in turn cause more warming. So this sets up a cycle of warming which keeps feeding onto itself. So let us see an animation which shows an example of how these feedback mechanisms work.
Did you know that one of the biggest causes of climate change is climate change itself? It may sound strange, but as the Earth's surface temperature has gotten warmer, natural feedback loops have been set into motion that are making climate change worse, even without additional human interference. How do we know this is happening? Well, in the past few decades, scientists have noticed something peculiar. Although the Earth's surface temperature has risen by 1 degree Celsius on average, the Arctic Circle is warming at least twice as fast as the rest of the world. In fact, in June of 2020, Siberia, which is normally one of the coldest places on the planet, experienced a record-breaking heat wave, with temperatures reaching 38 degrees Celsius, or over 100 degrees Fahrenheit. This accelerated warming is due to a phenomenon called Arctic amplification, and is the result of many natural self-reinforcing feedback loops. Let's take a closer look at some of these loops and see how they exacerbate the impact of climate change at the Arctic Circle. The first feedback loop is probably the one you'll hear about most often. It revolves around the albedo effect. Albedo is a measure of how much of the sun's radiation is reflected back towards space from Earth's surfaces. Different surfaces have different reflective properties. White areas like snow-covered land and floating sea ice reflect the sun's radiation. Dark areas, like the ocean water, absorb the sun's radiation and heat up. Due to man-made climate change, some of the white ice in the Arctic Circle has melted. With less ice present, more of the sun's rays are absorbed by the dark water, causing the ocean to heat up and more ice to melt. As you can see, this loop reinforces itself, accelerating the consequences of warming in the Arctic Circle. Another problematic feedback loop is the melting permafrost. Permafrost is a thick underground layer of frozen soil, rock, and dead organic matter that has remained completely frozen for at least 2 years straight. However, as the Earth's surface temperature has been increasing, the permafrost has been melting. The organic matter in the soil begins to thaw out and decay. Millions of soil-dwelling microbes metabolize the organic matter and release carbon dioxide and methane into the air as a byproduct. These greenhouse gases contribute further to the warming in the Arctic Circle, causing more permafrost to melt in another self-reinforcing loop.
So there are several such feedbacks, and but we will focus on the most prominent one, which is the sea ice melting. So just to give you some numbers, like if there is sea ice, it basically reflects 85% of the sunlight which falls on it. But if there is water, then it absorbs 93% of the sunlight. So how does the sea ice extent looks? So if we compare from March 1985 to March of 2021, we see that there is a severe reduction in multi-year ice, which is the white color. You can see how drastically it has decreased, and that basically means that there is more water now, which is absorbing more heat and basically will enhance the warming in the Arctic. So this warming, sea ice melts due to processes both from above and from below. From above, it is very obvious that if the air temperature rises, it basically causes the sea ice to melt. But from the bottom, it's less obvious. There are large scale oceanic currents which are bringing heat from the equator towards the poles. And this heat also causes the sea ice to melt. So let's see. So this graphic shows that there is water coming from Atlantic and there is water coming from Pacific. And both of these waters are warmer than the local waters in the Arctic. And both of them cause the sea ice to melt. So let's look at another video which shows how the oceans are contributing to this melting of sea ice. With this, I will end the first part of the talk, and I hope I was able to convey following key points from the section that there is enhanced warming in the Arctic compared to the rest of the world, a term called Arctic amplification, which you are very likely to come across if you read or hear about climate change in Arctic. And this enhanced warming is due to several feedback processes. So what we mean by feedback processes is the processes that are that are occurring due to climate change and which are causing more climate change in turn. And melting sea ice is one of the most prominent feedback cycles, and where warming melts sea ice, which in turn enhances the warming and melts more sea ice, and so on. And the sea ice melting is occurring both due to rising air temperatures and from below due to the heat carried by the ocean. So this is the role that we want to focus on, that the oceans are also carrying heat, which is melting the sea ice in the Arctic and enhancing the warming in the Arctic. So which brings us to the second section. So how do we study these processes? How do we study what is happening with the ocean and how it is contributing to the warming in the Arctic? So one of the most basic tools is the CTD, which is conductivity, temperature, and depth. So it's basically is host of sensors, which there are multiple sensors available now. So you can add several chemistry and biological analysis as well. But the basic instrument is for measuring vertical profiles of salinity and temperature. Let's see how it looks to take a CTD cast in the sea ice. Okay, so the limitation of the CTD instrument is that we can only cover few locations at few times due to the need for manual operation. So there is a better network available, which is called Argo network, which provides better coverage by eliminating so much manual operation, basically by using robotic CTDs. So let's see how this Argo network functions. think the Argo network is like a really beautiful example of international collaboration where like nations worldwide put these instruments in the water and they maintain them, and this allows um, development and maintenance of a data set which is really essential to understand how the oceans behave. Okay, so we come to the next set of tools, which is moorings, which is basically collection of instruments that are connected to a cable and they are anchored to the sea floor. So the advantage is that we get continuous measurement in time compared to CTD, but there is a disadvantage that these moorings are, of course, limited to very specific locations. So we have to really design well like we have to choose the locations really carefully so that we are able to study the phenomena that we are aiming to study. And like the deployment and recovery of moorings is quite exciting. And I hope the next video gives you a flavor of how this mooring operation looks.
So today is our first day of science, so we're super excited. After a week of transiting a very long, slow road to get here, we are ready to do science. So the first thing we're going to do is we're going to put this mooring in the water. It's a big weight at the bottom and a big floaty ball at the top, and we attach a whole bunch of instruments to the line, and we're going to leave it in the ocean for the next 3 weeks. So there's a bunch of different instruments on here. One of the things that's comparatively less common is that we have something called a McLean profiler. So it's an instrument that's like robotically crawls up and down this line. So it just has a little motor and it grips onto the line and goes and crawls up and down. But it gives us these beautiful continuous profiles of temperature and salinity and ocean currents. So we gradually pay out the entire length of the mooring and the whole thing floats on the ocean surface. Then we drag it to exactly where we want to put it, and then the grand finale is we put the anchor over, and it just goes down with a big splash, and then pulls the whole rest of the mooring down with it. So then the anchor ends up at the bottom, the float ends up on the top, and all the instruments hopefully are in their places in the middle. We put it out and wish it good luck and hope for the best, and we'll see it in 3 weeks.
So I hope the sound was clear, but basically what usually happens is that you start putting out the instruments first, and that then at the end you basically cut the rope connected to the anchor, and then anchor falls down and pulls everything together, and it is maintained like it maintains the straight sort of line because of these floats in between. And so you have sensors in between and which measures the water properties. Okay, so we come to the last set of tools I will talk about today, which is satellites or remote sensing. And this graphic is from European Space Agency, which shows what all data they are using from satellites to study the Arctic amplification. And they are taking data of sea ice from surface temperature, land cover, altimetry, ecological indicators, soil moisture, etc. And all these are the feedback mechanisms which we talked about before, but the main one is, of course, sea ice. Okay, so the first thing to make clear is that, of course, this is not an exhaustive list of the instruments. I just basically these are the very basic instruments which are used in physical oceanography. And of course, there are limitations to all these instruments and tools. For instance, CTD gives data in depth, but it has limited coverage in space and time. Moorings give data in depth and for longer time than CTD, but it is limited for very few locations. Satellites cover a very large area, but they are only limited to the surface, so we don't get what is happening below the surface. So like for any scientific inquiry, basically it's best to use all the data set that is available, and of course there is never enough data. So which brings us to the last section of the talk, and I will show you some example data from our own observations. So to start with, basically this is the Svalbard area where we conduct our studies. And if you see the large scale currents, it's basically the Atlantic water inflow that affects Svalbard. And this is the zoomed up map of Svalbard, and the area that we study is Hornsund, which is the southernmost fjord on the Svalbard. So this is the coastline of Hornsund, and what you see, the dots are the CTD stations. So these are the locations where we have taken CTD data. And the red colors indicate this is where we have found warmer waters which have originated from Atlantic. So if we see in depth and we go from the mouth of the fjord to deeper part of the fjord, so we see, so this y-axis is the depth, and this is the distance from the mouth. And the orange and red color indicates the warmer water. So you see that below 50 meters, we have large inflow of warmer waters. So when we say warmer waters, what needs to be understood is that it doesn't mean that the temperatures are 20 or 30 degrees Celsius. What it means is that these waters are warmer compared to the local water in Arctic. So the sea ice starts forming at minus 1.8 degrees Celsius. So if we have water temperatures which are 2 to 3 degrees Celsius, this will still hinder the formation of sea ice. And another process that happens in fjords is that we have glaciers which are terminating in the water. So if we have such large quantities of warmer waters entering and interacting with the glaciers, we have more melting in the glaciers itself. So let's see how that process works.
The sheet of ice that covers Greenland contains enough frozen water to raise oceans by 25 feet across the globe. As the planet warms, glaciers melt, causing sea levels to rise. But not all of that melt happens at the surface. In the summertime, rivers and pools of meltwater find their way down through the glacier to the bed below. From there, the water runs beneath the glacier until it reaches the ocean. Because meltwater contains no salt, it weighs less than ocean water and rises up the front of the glacier in what scientists call a plume. Around Greenland, oceans are cold and fresh near the surface and warm and salty at depth. As the plume rises, it draws in the warm, salty water, melting the glacier face from the bottom up. Eventually, a piece of the glacier breaks off, making an iceberg in a process known as calving. As the oceans warm, calving speeds up, causing glaciers to retreat and flow faster. Faster glaciers dump more ice into the oceans and drive sea levels higher across the globe.
I think this is my last slide, and I will basically will end this talk with the Arctic Report 2022, which summarizes the climate change in Arctic and what are its potential effects.
Human-caused climate change is having an ever-increasing and profound effect on the Arctic. From the ocean to the air, warming trends are continuing, and air temperatures in the Arctic are rising faster than the global average. In 2022, average annual surface air temperatures were the 6th warmest since 1900, with the 10 warmest years all occurring since 2011. Sea ice is thinning, far below conditions that existed 30 years ago, and older ice remains scarce. This loss of sea ice has enabled more shipping through the Bering Strait and Beaufort Sea, bringing with it more human-made debris, increased underwater noise, and the risk of potentially catastrophic incidents, such as oil spills. All of this activity has wide-reaching impacts on Arctic ecosystems. Seabirds are natural indicators of the health of marine ecosystems, and in 2022, Bering and Chukchi Sea communities reported the 6th consecutive year of seabird die-offs, most likely due to starvation, and coinciding with the loss of ice in those areas. Prior to 2015, seabird die-offs were rare in Alaskan waters and were usually wintertime events linked to disease outbreaks and above-average ocean temperatures. And both of those factors are projected to increase in coming years. Rainfall has also been increasing and likely transforming Arctic regions from snowfall to rainfall-dominated climates. In 2022, this was most apparent in eastern Greenland, Svalbard, and northern Norway, and in the central Arctic, with more consecutive wet days generally coinciding with reduced sea ice coverage in warmer months. Extreme weather, from heavy rainstorms to drought, has become more frequent, and the impacts of these events can be disastrous. At the peak of an unprecedented September heat wave over Greenland, more than 1/3 of the ice sheet's total surface was melting. A potentially large source of sea level rise is melt from the Greenland ice sheet. As warmer air and warmer water continue to melt the ice, impacts to ecosystems and communities within and far beyond the Arctic are already underway. The evidence is clear. Human-caused climate change is transforming the snowy and icy Arctic into a warmer, wetter environment. To limit these harmful consequences to the Arctic and beyond, it is essential for society to reduce greenhouse gases worldwide.
Sorry, so that was my last slide. So I hope I was able to convey some of the concepts of how there's oceans are playing a role in the contributing to the warming in the Arctic, and like why is it important to study such processes. So thank you for your patience.